The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
All right, in the meantime, let me introduce the next speaker. It is Mrs. Beth Brueggen, and she's going to be talking about behavior of non-rectangular reinforced concrete walls. And her presentation actually is with Professor Flange from the University of Minnesota, who unfortunately couldn't attend this session, but her former student, Beth, who did actually a lot of the work in the lab, and she's going to make the presentation. So.
Thank you. So I'm going to be talking about part of my PhD research with Kathy, which was developing a simplified modeling procedure for reinforced concrete structural walls. Kathy does send her regards and say that she was proud to be part of the Illinois Mafia. That is her in the blue shirt up there. That is Art Schultz. Professor Krager is in there somewhere, and I forgot who the other people were, she told me. So we'll start out with an introduction of the research project as a whole and our goals and then talk about the simplified modeling procedure I developed, how we validated that, and then summary and recommendations. The experimental portion of my research was load testing of 2 half-scale T-shaped reinforced concrete shear walls. While Professor Krager mentioned in the last session that they accidentally tested a T-shaped section and regretted it, we intentionally did. NTW1 was a 4-story sub-assemblage from a 6-story prototype building. We applied a moment at the top to mimic the shear-to-moment ratio of the 6-story building. Reinforcing was continuous over the height. It was concentrated in the boundary elements, and the confinement spacing was relaxed from the requirements of ACI 31802, which was then current, but it would be consistent with the new requirements in 31811. Specimen NTW2 was a 2-story sub-assemblage, so we imposed a much larger moment at the boundary to maintain the same shear-to-moment ratio. It was nominally identical, except we installed lap splices just above the first floor level to represent more realistic construction. We used uniformly distributed longitudinal steel in the flange to help with crack control. And we expanded the confined region a bit in the web tip because when we tested NTW1, we had some web crushing failures. This is the white here is the plan view load path we imposed on the specimens. The yellow dashed is a predicted failure surface from John Juan Sri Ramaletti's OpenSeas model. So in this plot, down would be flange and compression, up flange and tension, and left and right are flange direction loading. And these walls were instrumented so that we could separate the contributions of shear deformation, flexural deformation, and strain penetration from the total wall deformations. So if we go back to the performance-based engineering philosophy, we have these categories or places along the behavior of the wall, and those have been related to damaged states and needs for repair. Then to use this in design, we need to connect all of this to some engineering limit state that we get out of our model. For existing modeling tools, for simplified models, the FEMA 356 updated to ASCE 41 supplement, and then the Hines bridge pier model from UCSD, and then also more involved models, Letty's Open Seas wall model, and other finite element based approaches. So the simplified modeling procedure I developed includes both a load versus deflection relationship for pushover analysis and a framework for the prediction of the damaged states. Our desired capabilities of the procedure were, number one, it needed to be appropriate for general design use, so it could not involve abacus. But we wanted something that was more precise than the FEMA 356 and ASCE 41 model. We wanted it to be generalized enough to be applicable to any flexural wall geometry, including rectangular or flanged walls, not necessarily symmetric walls, any height, any length, the only requirement being that it be a flexural wall and not a squat wall. We did not want it to be sensitive to a particular detailing. We wanted it to be applicable to any loading direction, whether that be orthogonal loading or skew direction loading. And we wanted it to be transparent enough so that we could, or others could, add terms as needed. We named this the FSSP integration model to abbreviate flexure shear strain penetration. In hindsight, we should have come up with something more creative that was easier to say. It is based on a flexural section analysis, which you can get out of, we use John Wallace's BIAX. There are many other flexural section analysis programs out there. From that, you've got your flexural component of deformation, which you get from integrating your moment curvature twice. Shear component, calculating from crack shear stiffness and flexural stiffness, and then the strain penetration component, calculated from the longitudinal strains at the base. So for the flexural component, take your section analysis and calculate your moment curvature relationship. Integrate it twice. That's pretty easy, pretty straightforward. We have all sorts of great tools to do that with. This does, number one, assumes plane sections remain plane, so we're neglecting shear lag in flanged walls. That could be added in with an effective width or other adaptation. And it neglects tension shifting, which is when you have diagonal cracking that increases your plastic hinge length and therefore your deflections. There are also some challenges with this approach in finding your post-peak behavior. So if we use measurements from NTW1, on the left is the flexural displacement of just the first story of the wall. On the right is the flexural displacement at the top of the specimen, so the top of the fourth story. And on each plot, this is just unidirectional loading, flange tension, flange compression, going negative direction being flange compression, and going positive direction, flange and tension. Because there is about twice as much reinforcement with the flange and tension, you do have a much larger load capacity on this side. And failure in these was we crushed our web, buckled the bars in the web tip, then when we loaded in the opposite direction, the buckled bars snapped. You can see these red dotted lines are the output of the model taken from integrating moment curvature twice and using the measured as-built material properties. Shear demands, if we consider a simple cantilever wall, you have constant shear over the height, and of course your moment is triangular. If you look at shear deformation, you do not have constant shear deformation over the height. Shear deformation is concentrated down here in the base in the plastic hinge region. And if we look at real data to study this, this is a view of the first story of our specimen at the end of testing with all of the cracks marked. And on the left here, the inner story shear displacements. The two black dotted lines, the steep one is the uncracked shear stiffness. The shallower dotted line is an estimated crack shear stiffness assuming 45-degree crack angle. And so you can see the first story had a large amount of pinching and very large shear displacements. You can also see that it was quite a bit softer in the flange and compression direction, which put a large amount of the web in tension. Cracks were shallower, so that is expected. Second story had some yielding, but much less flexural damage and was much stiffer in shear. And the third story was nearly elastic in the flange and tension and similar to the crack stiffness, flange and compression. So our proposed method to deal with this in a simplified manner is to set the shear deformations proportional to flexural rotation, or if you take a derivative each of that, you've got your shear strains proportional to your curvature. So then we just have to define a proportionality constant. If we use the crack shear stiffness and the flexural stiffness at yield, here's the expression for 45-degree cracks, and there are additional terms to add to this for other crack angles. And then take the ratio of flexural stiffness at yield divided by shear stiffness times your shear span. So if you had a wall that was loaded at each story level, you could use a moment to shear ratio for that. Calculate your constant. And here's how the model works out. The green dotted line is predicted from the calculated rotation, which we get from our moment curvature analysis. The red line is predicted from the measured rotations in the lab. You'll also notice that we have different shear constants, flange and tension versus flange and compression, because we have different flexural stiffnesses each direction. In the flange and compression direction, we have good correlation. Flange and tension, the model is predicting softer. That it likely has to do with the web primarily being in compression and being stiffer in shear. Then finally, strain penetration, we are to simplify this as far as possible, assuming plane sections remain plane, which would mean that you assume that somehow we have an impossible physics problem over here in the compression block. And assuming that behavior in tension and compression are similar, basic geometry here to calculate a rotation at the base, so a rigid body rotation at the base from a slip of the tension steel. Assuming a constant bond length and strain gradient, you can then do some algebra and come up with this expression for your rigid body base rotation, where your strain, critical strain, is the strain at the base from your moment curvature analysis. Put that all together, and we have decent correlation. You notice here from our test results, the behavior in the lab was, for strain penetration, was not as organized as the flexure and the shear, but we do capture the general shape fairly well. And then the final step of this would be, once we've got our pushover curve to predict damage levels. So existing documents, FEMA 356, ATC 58, and others have correlated a general qualitative damage level with a performance level and given it a name. And then other researchers, including the group at Washington, have said, and this they put together for concrete columns, although a lot of the repairs are similar. So using this framework, correlating for each performance level and damage level, required type of repair, and local engineering demand parameter, i.e. something that you can get out of a structural analysis to use in your design. So, for instance, for a median occupancy level, our repair might be epoxy injection of cracks. We predict cracking based on the tensile strain in the steel. Getting into the minimal and moderate and life safety, we're looking at replacing concrete cover. So, in determining that based on the cover concrete compressive strain or the core concrete compressive strain. And finally, at the collapse prevention level, you're looking at needing to replace the section. So based on my T-shaped wall test at the University of Minnesota and Ben Johnson's 3 rectangular wall tests, since then we have a few more data sets to use for calibration, which may lead to a revision of these numbers. We can provide some threshold values for the designer to use to estimate the damage level. Our test did allow us to distinguish between steel concentrated in flanges and steel distributed across flanges, providing much better crack control, which allows a larger strain prior to requiring epoxy injection, and then doing spall repairs once you spall your cover, and at some critical core concrete strain needing to do more extensive repairs, and finally you replace the section when your model is indicating a post-peak loss of capacity. We validated this model against available data sets, including comparison to NTW1 and NTW2, comparison to 6 tests reported in the literature. We also compared to the existing simplified models. All of this validation was based on the reported as-built material properties. A designer would need to make some estimate of the as-built material properties, concrete overstrength relative to specified, strain hardening of the steel, etc. In general, we predict the moment capacity very well. That's largely because we have very good tools and ability to predict flexural behavior. We generally under-predict the displacement capacity. Sections we used, in addition to our T-shaped walls, Ben Johnson's rectangular walls, John Wallace's T-shaped walls, and Sharon Wood's C-shaped walls. All of the walls that we use for validation do have aspect ratios between 2.5 and 3. And then Eric Hines' bridge pier specimens, which are very different geometries. Whoa, where'd we go? With these barbell walls with large amounts of reinforcing in the boundary elements. We also compared to the existing simplified models. So if we compare the red lines being the FSSP model that I developed, the green being FEMA 356 updated to ASCE 41, you can see it's the FEMA 356 model neglects your strain hardening. It's generally too stiff in the pre-yield region because it's neglecting everything except flexure. And it's very conservative, which the developers of that model intended to be very conservative. You can see we captured the overall shape fairly well, including the capacity. The specimens failed in the flanging compression direction long before any model predicted they would, because that failure was preceded by buckling of the web tip reinforcement in compression. This slide shows the flange direction loading, which in all cases our flange direction cycles were after damaging the wall to a similar amount in the flange tension, flange compression direction. We're underestimating drift capacity significantly here. In summary, we're taking advantage of the relative ease of modeling flexure compared to shear and strain penetration. And we developed this by using a flexural analysis. It's applicable to a very generalized case as opposed to the existing tools, which have been primarily for rectangular walls. We are more accurate than the existing walls. We've developed a framework for predicting the damage levels and validated with tests with aspect ratios of 2.5 to 3. One downfall of this approach is that we're not tracking damage due to the prior load history. Some possible modifications and improvements. We do need to do some additional calibration of the threshold strains for damage prediction using a larger data set, and now That data, the available data set is now larger than when I did this work. Efforts to incorporate shear lag effects would be useful for flanged walls. We considered adding an artificial plastic hinge length to represent tension shifting and avoid our under prediction of the ultimate drift capacity. Consideration needs to be given to improving the prediction of post-peak behavior for predicting stability beyond in the collapse prevention range, and refinements to the shear crack angle prediction and strain penetration model would be appropriate to increase the accuracy of the model. And with that, I will take questions.
Any questions for Beth? I assume all presentations have been so great that very, very few questions have been asked. So thank you.